Hey everybody, how you doing? My name's Ricky, and me and my partner Max will be presenting Convex Learning with Invariances today, our implementation project. So I just want to start with the big idea. The big idea is basically a platonic world of forms style recognizer. These authors wanted to build a learning machine that was invariant to transformations. So something that basically had an idea in its head about the canonical object, concept, whatever it happened to be recognizing, independent of whatever instantiation it happened to take in the world. So a chair over there is the same as a chair over here, no matter what orientation it is, because I have an idea of a chair in my head and a computer doesn't, but these authors would like to teach their system something like that. Um, Here's just some examples of some transformations. This was for handwritten digits. You can see shears, rotations, scalings, that kind of thing. And they trained their invariant SVM algorithm against a few other algorithms. They had a standard SVM and then a virtual SVM. Um, they There have been other methods for this invariance learning, but they haven't liked a lot of them because of either too restrictive of a problem formulation or inefficiency in essentially number of support vectors it uses. As you can see by the red line there, the virtual SVM was a prior method and it just uses a ton more support vectors than their invariant SVM. One really interesting aspect of this is they form their algorithm in terms of searching for the worst case transformation that the algorithm could try and classify, and then adding that as a support vector. This becomes a problem in both very large and infinite search spaces. But the authors come up with this nice trick where you only actually have to give a recipe for finding the worst case margin violator. You don't actually have to search over the entire space exhaustively. This comes into play in the spam filtering experiment with their F-scale algorithm, which we present a little later. I just want to give you a quick how they form the problem. They use structural SVMs, which formulates prediction as a maximization problem. You basically have this compatibility score function, I like to call it, f of x, y. You give it an x example and a y label, and f of x, y basically gives you back a number that tells you how compatible label y is with example x. If you go and maximize that function over the entire space of labels and give back the top label, the top scoring label, you'll basically have your prediction. In our case, f of xy is a kernel function, so it's a feature map, a joint feature map actually interproducted with a weight in feature space. But that's essentially all you need to know about structural SVMs. They stuck to structural SVMs quite closely in their algorithm, and we'll see that coming up. Just a few more invariance transformation examples. For spam detection, emailers could be changing words or letters, but not actually changing the concepts. And then in image recognition, the digits could be in different positions, but that doesn't necessarily mean that they're different digits. So now to get on to the algorithm and our actual implementation of it, they formulate their SVM struct type algorithm. All SVM struct type algorithms are in the form of column generation. The kernel matrix is generally too big to enumerate the entire thing, or you have an infinite search space problem where you just can't enumerate it all. So they proceed iteratively, basically cutting down their constraint, or they pick support vectors one example at a time until they can't find more violating support vectors. So the first thing that you need to do is initialize some data structures for keeping constraint sets for each training example. So in our implementation, we initialized an S set, which was basically a bunch of lists, one list for each training example, where transformation label combinations would go once they were found by the algorithm. Some other ones were defined, but they were more for convenience, just so we had transformed picture vectors and labels around to build the optimization problem. So the actual algorithm is basically built in 4 parts. This first part here, the f of x prime y prime, is going to be your compatibility score. Though it's modified from the compatibility score in general. Instead of looking at the entire space of Lagrange multipliers, those little alpha things, you actually only look over the subspace of Lagrange multipliers that you found that are consistent with the transformation label combinations that are in the current training examples working constraint set, that SI thing there. And then basically you only use those terms to define your difference of kernels. So you basically are only using the alphas that are relevant for your current training example, the support vectors. Now, this is actually where we got hung up in the implementation project. We got past this in the algorithm, of course, but this was the broken part. We couldn't figure out how to track our alphas adequately. If the quadratic program gives you back a big list of alphas, and the certain alphas need to be associated with certain training examples, you need to track those with indexes and lists, and that is what we didn't quite work out by the end, or hadn't quite worked out by the end. But if you were tracking everything correctly, this lambda function would define that compatibility score. It's the dot product, or the inner product of the alphas that are in your constraint set with the difference of the joint kernels of the actual training example and the labels. Well, the first term is the actual training example, and then the label that you're looking at the moment. So the whole thing is a list comprehension over the transformation label pairs in your working constraint set, minus the joint kernel for the actual label of that training example. If you sum that all up for all of your training examples, you'll get a scalar for the compatibility score. The joint kernel, this isn't the whole function, but the joint kernel is defined as the outer product of the y labels represented as logit vectors times the RBF kernel of the actual example matrix. The next part is the actual optimization to go find the worst case transformation that your algorithm could classify. So we turn from looking at the subspace of transformation label combos that are in the current examples working constraint set to looking over all of the possible combos SY using the function that we just built up. That compatibility score, we try and find the highest scoring one. And if you were doing this in code, you could do this with a list comprehension. So, for example, in the handwritten digit experiment, they had a finite search space of 220 label transformation pairs. And since this is pretty small, you can just enumerate all of them, do all of the computation, and then take the max of that, or at least the index max, and store the most violating constraint that you've seen so far, because you could potentially want to use that as a support vector if the if check passes later. The third part is just computing the slack variable. So we're back to looking at the restricted subspace of the working set of the current training example. We take basically the worst constraint transformation that we've seen so far, and then in this if statement down here, we compare it to so if you were to do this, you could just use the functions that you've built up already, go through your working constraint set for the current example, and then store your slack variable. We do the if check, basically just plug the equation in, check it against your slack variable. It's a pretty simple if statement. I don't have a line of code for this in the example, but the next part is to actually do the quadratic program. There's two ways of doing it. You can either do it just with respect to the z's in the working constraint set, or you can do it for all of them. The authors suggest doing it just for the z's in the working constraint set. We did it for all of them. This basically just boils down to building the QP matrices. The quadratic term is your joint kernel with all of the constraints. If you were doing all of it, just the subset of constraints if you were doing a subset. Your linear term is a regularization parameter. We set it to all ones. You need a negated identity matrix to have positivity constraints, and then a vector of all ones to make sure that everything sums up to 1. You can plug this into any solver. We used quadprog, and then when you get the alphas back, you have to store them intelligently. And this is once again where our algorithm went wrong. We weren't tracking our alphas correctly, and back up in the dot product of the F compatibility function, we weren't able to pick out the correct alphas from our vector to actually do the compatibility score prediction. So the implementation of F-scale, this one is interesting because this is a computational recipe for searching an infinite search space. They basically have a recipe for searching the transformation space where you don't need to search it exhaustively. If you just follow this algorithm that we have implemented, you can check Bitbucket. It will go and search for that argmax problem, that second part of the algorithm, without actually having to go and exhaustively search the space. So just in summary, I want to say that this helped us learn a lot about convex optimization and actually learning models and tuning parameters. Even though we didn't actually get the functioning algorithm, we learned a lot about convex optimization that we didn't know before, and also the challenges of doing not exactly robust estimation, but estimation against inputs that aren't perfect, let's call them. And with that, I'll just say thank you for a great semester.